In this video we're going to be looking at rotating objects. So if we want to describe the motion of a rotating object, it's very inconvenient to use the regular displacement, velocity, and acceleration as we have been using so far. Because if we have an object that's rotating, to describe the regular displacement, velocity, or acceleration, we have to pick one point on this object to analyze. And as you can see, say after the object has rotated this much, these 2 points on the object have traveled a different distance. So this point further out from the center or the axis of rotation has a greater displacement and therefore greater velocity and acceleration than this point that's closer to the axis of rotation. So we need to come up with quantities to describe the rotation of this object as a whole instead of just one of these points on the object. So the first quantity is angular displacement, and it basically measures the angle that the object after the object has rotated. So we use a reference line, say here, and then after rotation we look where that line has traveled to, and this difference in angle is the angular displacement. And we measure this in radians, and radians is just the ratio of this arc length of the angle and then over the radius of this circle. So radians is actually a unitless quantity because arc length and radius are both measured in meters, so the units cancel out. But we put a rad here just so we don't get confused. And the convention for all of these angular quantities is that the positive direction is counterclockwise and the negative is clockwise. So angular velocity is just the change in angular displacement over time, and it's represented by this kind of W, which is the Greek letter omega, and the units are radians per second. And then we have angular acceleration, which is the change in angular velocity over time, and it's represented by this letter alpha, and the units are radians per second squared. So all of the kinematics equations that we used at constant acceleration can also be used for rotational motion if the angular acceleration is constant. So you can see we just take all these equations and replace displacement, velocity, and acceleration with angular displacement, angular velocity, and angular acceleration. So sometimes in a problem you'll get some of these quantities, such as this angular displacement, in revolutions instead of radians. So a revolution is just the time it takes, well, not the time, it's one full turn of the object. So when you solve these kinematics problems, you have to make sure all your quantities are either all in revolutions or all in radians. Now, sometimes in more complicated problems, you need to be using radians, so it's always safe to convert to radians if you're not sure. And you do this by recognizing that one revolution is just 2 pi radians, because there are 2 pi radians in a full circle. So we also can convert between the rotational quantities of the rotating object and the linear quantities of a single point on the object. So the velocity of any of these points is just the distance it travels, which is the arc length, since it's moving in a circle, over time. And so from the if we use the definition of a radian, which is the angle equals arc length over radius, we can get that if there's a change in the arc length, it's equal to the radius times the change in the angle. So if we plug this in for the change in arc length in this formula, we find that another way to express the linear velocity is radius times change in theta divided by change in time. But we know that this change in angular displacement over change in time is just the angular velocity. So the tangential velocity of any point on this object, if this point is a distance from the axis of rotation, its velocity is times omega. And then we can also find that the tangential acceleration of a point is times alpha. And so in these equations, the angular acceleration and angular velocity have to be in radians, because we use this definition of a radian to derive these equations. So this is when you need to convert from revolutions to radians. And so remember, when you studied circular motion, you learned that the acceleration of the object is called the centripetal acceleration, and it always points to the center of the circle. But if we have a rotating object with angular acceleration, the points that are moving around are no longer in constant velocity, which means they aren't in uniform circular motion anymore, because the velocity is changing magnitude as well as direction. So in addition to this centripetal acceleration, which changes the velocity's direction and points to the center of the circle, we have this tangential acceleration, and this component changes the velocity's magnitude. So since the total acceleration consists of these two components, the centripetal and tangential, the total acceleration no longer points to the center of the circle, because it's the sum of these two acceleration vectors. And so the centripetal acceleration, which is v squared over can also be expressed as times the angular velocity squared. So now let's look at a couple examples. So say we have a Blu-ray disc and it's spinning at 27.5 radians per second, and it's slowing down with a constant angular acceleration of negative 10 radians per second squared. So we want to know what is the final angular velocity and angular displacement after 0.3 seconds. So here we just used kinematics equations. So to find the final angular velocity, we use this equation. Final angular velocity equals the initial angular velocity plus angular acceleration times time. And so we find that the final angular velocity is 24.5 radians per second. And to find the angular displacement, we use this equation, which is the equivalent of d equals initial velocity times t plus 1/2 at squared. And so the angular displacement is 7.8 radians. So here we have an athlete, and he's spinning a discus around in a circle with a radius of 0.8 meters. Remember, you have to convert any centimeters or anything to meters. And so at one moment, the athlete is spinning at 10 radians per second, and his angular acceleration is 50 radians per second squared. So we want to know the tangential, centripetal, and total acceleration of the discus that he's spinning at this instant. So to find the tangential acceleration, we just use times alpha, which is 40 meters per second squared. So this part of the acceleration is changing the magnitude of the velocity of this discus. And then the centripetal acceleration, which is changing the direction of its velocity, is times omega squared, which is 80 meters per second squared. And so the total acceleration is the sum of these two vectors, the centripetal and tangential acceleration. So to find the magnitude of the total acceleration, we use the Pythagorean theorem. And so we find that the total acceleration is 89.4 meters per second squared. And it points somewhere in between the two component vectors, not towards the center of the circle.